Next up, we have Dr. Mathias Sablé Meyer, who is currently a postdoc in Tim Barron's lab at UCL, and prior to that completed work with Stan Dehaene at the Collège de France and Neurospin. Engaging with Dr. Meyer's work is a constant joy, not only because it spans an incredible array of methodologies, from experimental psychophysics to historical probes to fMRI and MEG, I believe, as well, but also because it allows us deeply to engage with what it means to be human, as evidenced by the fact that you will see in almost all of Dr. Sablé Meyer's work a cave painting. Please take it away.
Thank you so much for the very kind, detailed introduction. Here I'm not going to talk at all about comparative work. I'm only going to talk about human work, but I'm happy to chat about the rest offline afterward. Thank you so much for having me. I know this is the Mathematics of Neuroscience conference, but I'm going to give you a little bit of neuroscience of mathematics instead. Don't worry, there'll be theory and model and things to connect back to the theme. More specifically, I'm going to talk about the human cognition of geometry. And when I say geometry, you might be tempted to trace it back to something like Euclid 2,000 years ago, who formalized some elements of geometry. But really what I'm interested in is a much broader set of human abilities, exemplified by things like these spiral engravings 5,000 years ago in South America, these zigzag patterns engraved on pieces of ochres in South Africa, or these zigzag patterns on pieces of seashells 500,000 years ago. One thing that they have in common is that if a paleoanthropologist finds them, they're not going to think that it's been carved by the local tiger, right? It seems almost trivial that this is a human production. And it ranges across really wide geographical areas and timelines. In fact, there's another timeline you can rewind, and that's the developmental timeline. If you ask children to draw a person, you'll get something like this. I think everyone agrees that this is visually completely implausible, but typically parents will reward this. And similarly, if you just give them a piece of paper and a pen, they will scribble, and then they will explain that these are railroads or trains. And post hoc, you can sort of see the connection, but again, visually, this is sort of absurd. And I'm interested in the mechanisms underlying these processes. And the simplest thing you can do nowadays is just take participants, put them in the scanner, in an MRI scanner, show them a bunch of visual stimuli belonging to different categories. So for example, faces, tool, objects, houses, but also text or geometric shapes, and look at which area differentially respond to these different categories. And if you look at which areas are sensitive to geometry versus other categories that have a single object on screen, you get these kind of activity maps. So just to give you, like, this is an inflated human brain, right? You see both the bottom part here and then the two hemispheres. This is what you get. So in red are areas that respond to geometry more than other categories. In blue, areas that respond less. This is a stable kind of pattern because if you do the same experiments with kids, you get pretty much the same result. And there are two main features that I want to talk about here. The first one is the massive underactivation in the ventral pathway, the blue bit on the bottom side of the brain. And the other one is the red bit on the right hemisphere in the intraparietal sulcus. The ventral one is interesting because this is typically where visual categories are processed. And by sort of carving it out and looking into it, we can reject a bunch of hypotheses about how geometry is treated. So for example, you might think that it looks a little bit like script, like text, because it's like small lines on an empty background. But if you isolate the area that's responsive to text and you look at how it responds to geometric shapes, you get almost no particular activation. So what I'm showing here is the visual word form area that typically responds to words. You see that it is activated for words, that's the big bar in blue. It's also sort of activated for numbers, that's the bar in yellow, but you'll get almost no activation for geometry. You could also think that maybe geometric shapes are a human artifact. They look like objects for thoughts, so they might respond. They might be activating areas that typically respond to human-made objects, but that's not the case. You might think that when we pay attention to those, we're careful about small differences in visual perception, and it looks like faces, but again, that's not the case. Or things like houses, which is sort of our prototypical contrast for like object perception. And so really in the ventral pathway, there doesn't seem to be any area that particularly cares about these shapes. Conversely though, the area that we isolate in the intraparietal sulcus in both adults and children is far from being sort of a new finding. 25 years ago, this area was put forward as the place that cares about mental computations. So if you ask participants to do small number comparisons, you get a similar kind of activity. This is also an area where you find neurons in macaques that respond to numbers specifically. So you get neurons that are attuned to quantities like 1, 2, 3, and so on. And much more recently, some work argued that even when dealing with sort of very high-level math, so processing a sentence like the sine function is aperiodic and deciding whether it's true or not will elicit activity in these areas above and beyond typical language networks. All of this I find pretty exciting, but this is based on absolutely no task, and it doesn't really allow a sort of fine-grained carving of the processes underlying these representations. So the next thing to do is design a set of shapes that are matched for visual property, but range in number of geometric regularities, and then study how human differently responds to each of these shapes, and try to see if we can get a theory of their mental representation of shapes from this. And the simplest thing you can do is just from behavior. You display a bunch of geometric shapes. 8 of them are identical up to scaling and rotation. 1 of them is different. Participant's task is to find the one that's different from the other. And the intuition here is the more different shapes are in the mental space of participants, the easier it is to find it and the faster it is to find it. And so you get an empirical measure of the similarity or dissimilarity between shapes. And you can do this with any pair of shapes. You get a general dissimilarity matrix. And then the question is, does this matrix have any pattern? Can we explain its structure, and so on and so forth? And here I'm just going to present 2 models. One is based purely on geometric features. So for any shape, you count how many internal geometric regularity it has. And by this, I mean things like parallel sides, right angles, equal angle, sides of equal length, and so on. You do this for both shapes, and then you predict that a particular trial is as difficult as the shapes are similar. So it's as difficult as they share geometric properties. That's sort of the most extreme geometric feature, sort of symbolic model of these tasks that I can come up with. On the opposite of the scale of the spectrum, you can just take all these shapes and propagate them through a neural network of object recognition. I'm going to show results from CoreNet here, but you can take different networks and you get pretty much the same results. So you propagate all the shapes through the network, you take the activation vector, and you take the vector that's furthest away from the average of the other as the sort of behavior answer from the network to the question, which shape is the intruder? And again, that gives you a dissimilarity matrix between any 2 shapes. And so if you model human behavior, you find that both of these models are predictive of behavior, but crucially, the symbolic model is way more predictive of the behavior. And this is going to be useful because now we have a tool to sort of understand the mental processes underlying these geometric shapes, and we can go back to neuroimaging and trying to find their neural correlates. So the next step was record data of participants in an MEG, passively watching shapes, same geometric shapes, 1 per second, and the structure is a sort of block design, so you're going to have 30 squares, then 30 rectangle, then 30 of another shape, and occasionally you're going to have a shape that's different from the other, but really participants have no task, they're just sitting there watching shapes. And they sort of do this for an hour and a half. These are very patient participants. And the first thing you can do is, from the neural data, try to decode whether the shape that's currently on screen is an oddball or not, is an intruder or not. And this you can do. But not only you can do this, but if you train this decoder and then look at its performance across the different shapes, you find that finding intruders within regular shapes is much easier for the decoder than it is than finding an intruder within irregular shapes. And maybe from the behavior this is obvious, but it's always nice to see, in the complete absence of a task, a replication of a behavior result where, in a sense, intruders pop out really strongly within regular shapes, but not so much within irregular shapes. The other thing you can do is take the average sensor level data from MEG to a particular shape, like the rectangle, take the average sensor data for another one, like the rhombus, compute a distance between these two things, then do the same thing for each pair of shapes, then do the same thing for each time point, and now you have a dissimilarity, you have a neurally derived empirical dissimilarity matrix that you can play the game of modeling with the two models that I put forward before. And when you do this, you find that the early neural activity is well predicted by the sort of bottom-up visual model, but later on, there's a significant cluster associated to the symbolic or geometric feature model. Interestingly enough, these two clusters are like sort of similar in magnitude and duration and so on, but it seems like at the time at which they respond, participants rely substantially more on the symbolic model than on the neural network model. But in the neural activity, you see both one after the other. And you can also do some kind of fancy math to project back the sensor data back into cortical surface of the participants. You do source reconstruction. And if you do this, what you find is that the neural network model ends up being projected to the occipital cortex, which is sort of reassuring. But the symbolic model is projected to a much broader set of cortical areas that include the dorsal pathways, the IPS that we've seen earlier, but also dorsolateral, and I'm not showing it here, but medial frontal cortex. Cool. So just as a interim summary, the fMRI data indicates that just simply perceiving geometric shapes seem to activate a dorsal, typically math-responsive network in humans. And we can split this into a perceptual component and a symbolic component, at least for the shapes that I've shown so far. And we can separate them both in times and in localization in the brain. I like this. This is exciting to me. But this is all about a bunch of quadrilateral shapes, and this is nowhere near the kind of richness that I started this talk with spirals and lines of squares and things like this. And so the next step is, can we account for this kind of rich world of geometric shapes that humans care about? And to do so, I went back to sort of classic cognitive psychology literature on the language of thought hypothesis, with the idea that humans have a capacity to attach discrete symbols to concept and then combine these, possibly recursively. This is very visible in natural language, but the hypothesis that it's a much broader kind of competence in the human brain. It allows children to create new concepts by just recombining, or children or anyone really, to create new concept by recombining existing concept. So for example, the zigzag here might just be an alternating set of parallel lines. That's what I'm going to argue for in a second. And so under that view, understanding something really means figuring out an internal mental program that is going to generate that thing. That's sort of the core aspect of the language of thought hypothesis, which has been explained to some extent today already. And as you learn new concept, you add them to your sort of lexicon of programs, and so the reach of what you can understand grows as a function of how many mental objects you've acquired already. And how do you test this? I'm not going to go into too many details here, but what I did is completely commit to a generative language for shapes. So a program that generates geometric shapes. I'm happy to discuss offline about how you go about figuring one that is a plausible candidate. But the claim is the shorter a particular shape, the shorter the program for a particular shape is, and the easier it should be for all sorts of behavioral tasks in humans. And this is exactly what I tested afterwards. So you use this language, you recursively enumerate its program, you generate the associated shapes. And so for each shape, you have an idea of how complex it is according to this generative program. And then you test human behavior. And so what I went for is a self-paced delayed match to sample. So participants see a shape, then there's an empty screen, and then they have to recognize this shape within a set of distractors. But there's a twist here, which is that the amount of time that they spent looking at the first shape is self-paced. So participants press spacebar, the shapes come on screen. When they release spacebar, it disappears. And that's a really good introspective measure of how complex they think a shape is. So we measure this, but then we also measure accuracy and response time in the second phase. And the question is, does performance or encoding time correlate with the complexity of the shape according to that language? And this is what we find. So the longer the program and the higher the response time and the higher the encoding time. But of course, if you look at these shapes, you might immediately think, oh, but it's confounded by a number of other visual factors like gray level, high visual frequencies, and things like this. All of which have been proposed in the literature to be extremely important for vision. And if you add all of them as co-regressors, so you compute a bunch of visual features for each of these shapes and you add all of these into a GLM, what you find is, unsurprisingly, many of them are a significant predictor of human behavior. But crucially, the minimal description length, so the length of the shorter program that generates a shape, is still a significant predictor of behavior. So that's the orange bar here. I think committing to a language like this is useful because you can take it at face value and test predictions and move forward. But the language that I'm proposing is almost certainly wrong for a bunch of reasons. One of them is that it's unable to generate an ellipsis, and it seems like the kind of shapes that we would want to be able to predict. So stepping back from that particular proposal for a language, I also tested some sort of more general properties that I think alternative propositions should respect. And specifically, I'm going to talk about three that are somewhat straightforward, but still very informative. One of them is saying that the complexity of repeating a shape, the complexity of a shape repeated several times should only depend on the complexity of the shape and the complexity of the number of times, and it should not be a multiplicative factor between the two. Perhaps very simple, but always useful to put forward, the complexity of two shapes should be the sum of the complexity of the two shapes. The third one is a bit weirder. It says something like the complexity of drawing one shape out of small version of another, so drawing a square out of circle, should only depend on the complexity of the square and the circle and not any interaction effect between the two. And then you go about figuring a bunch of, like a few shapes of different complexity. You put them into these kind of programs. So for example, you repeat them, or you put any two side by sides, or you draw any one of them out of small versions of the other. You measure behavior on these kind of things, and you test whether your predictions hold. And again, I use the delayed match to sample task here. So they see a shape, they see nothing, they have a choice, and we measure all of the dependent measures. And the first result is pretty straightforward and reassuring. The complexity of repeating a shape n time only depends on the complexity of the shape and some encoding of the complexity of the number. This is true for encoding time, but also for other dependent measures. The complexity of putting two shapes side by side is only the sum of the complexity of the two shapes. But here there's a caveat in the model, which is predicted by the theory. If the two shapes are actually the same, then you're not really in a case of concatenation, you're in a case of repetition, so you need an extra term to account for this saving. And the same model holds true for the embedding. And here there's something really interesting that's happening, which is the complexity of drawing a big shape out of small version of another is the sum of the complexity of the two. But there is again a saving when the big shape and the small shapes are the same. And this is not something that I can straightforwardly predict because it requires your mental representation. So put another way, a square of square is substantially simpler. One way or another, your mental representation of a square, you're able to perform some sort of saving across the two scales of your representation here. And I think this is quite exciting. It's also sort of a challenge, both for a modeling perspective and for implementation, for mechanistic implementation of your representation. I usually have a slide here saying that program induction is difficult, but we can sort of do it, but not really, but it's hard, but it's cool. And I think that this is what we do, but then you've had a great talk this morning explaining this much better, so I can skip over this. But the take-home message is, it is in principle feasible, and then the question is, how do we do it? And that's a mechanistic question. So as sort of general conclusions, I think this provides converging evidence that the mental representation of shapes goes substantially beyond straightforward mechanisms of vision. You can sort of separately capture the visual or perceptual aspect of it, but you need some more kind of geometry-based or feature-based model to account for late mental representations. It seems to overlap a lot with networks that are typically found for maths in the human brain. And the mental representation of shapes is well captured by generative models if you choose your primitives well. And then the next question is something like, what if we go down one layer of the MAR hierarchy? How do neurons actually implement this? What's the substrate for all of this? And this is ongoing work that I'm doing in my postdoc that I'm happy to talk about. And with this, I would like to thank the organizers and everyone who collaborated on this project, who supervised me on this project, who I supervised on related projects. Thank you.